Yeah, is it visible? Is it visible?
Sir,
Yes,
Yes,
sir.
sir.
Oh, okay. As I told you in the last class that uh, matrix is an arrangement of some elements within certain rows and columns, and that matrix to construct, we must have elements. But if elements are not told you directly, and if it is defined with the help of a function, and that is, say here, this one, construct 3 by 2 matrix whose elements are given by this aij is equal to half into I minus thrice j within modulus. This is actually definition of the elements. This rule is given to have the elements, and you know, aij, as I told you, aij means every element of the matrix, where I indicate always row and j indicate always column. That means if we consider a11, it will represent a11. That means first row, first column, the position of the element, first row, first column. If it is 1 2 we consider, then it is first row, second column. So thus we can have all the elements from this definition, from this given rule. Now what is the size of the matrix to be constructed? 3 by 2. That means there should be 3 rows and 2 columns. So theoretically, let the matrix to be determined here. So it is assumed that the A matrix, it is assumed that the required matrix is of this structure. Definitely there are 3 rows and 2 columns. As we need to determine this matrix of order 3 by 2, so here it is considered a standard matrix, theoretically considered 3 by 2, 3 rows and 2 columns. As I told you, this suffixes indicates row. You know, this element a11, why it is a11? Because this position, this element is lying in the first row and first column. So I equal to 1, j equal to 1. Here this element lies in the first row, so it is I1, and second row it is lying, so j is 2. Similarly, this element a21 means the element is lying in the second row and element is lying in the first column, so it is 2 1. This element you see a31, that means this position is lying in the third row and first column, so it is 3 1. I is 3 and j is 1. So it is just assumed that matrix to be formed. If order is different, then accordingly we will consider this matrix. If there are 3 by 3 matrix, then we have to consider one column more. 3 by 3, 3 rows, 3 columns. Here it is 2 by 3, we need to determine, so 3 rows and 2 columns. That's why we have considered theoretically this one. Now, our convenience letting this matrix is, what will be the values of ij to be considered here? We can just observe this one. This is the rule from which we can have all the elements of the matrix. So in this rule, very simply, in this rule, we can put the value of ij. First of all, this first element, suppose we are going to compute. In the first element, the value of I is 1, j is 1. So just put here I is 1 and j is 1. And we will be having a11 element. It is I is 1 and j is 1. So within mode the value gives us 1. So first element will be 1. Second element A12, second element of the first row A12. If we put I equal to 1 and j equal to 2 here, so A12 is 5 by 2. So thus all these elements we can have in this way. Very simple calculation. The values of I and j just consider from here and just put in the rule. So A11, A12, A21, A22, A31 and A32, all these 6 elements we have got with the help of that rule. So simply if we put the values in the matrix, we will have the answer. So this is the required matrix. This is A11, it was A12, it is A21, it is A22, it is A31, this is A32. All these values we have written from this one. It's a very simple calculation. So this means whenever the elements of a matrix are given using a rule or function, then just considering the values of I and j, we can construct any ordered matrix. So any ordered matrix we can construct, but definition of the elements must be given distinctly. It's very simple. Now let's go through some types of matrices. You see here types. So in a matrix, as you know, just there are some rows and some columns, and based on the nature of elements, sometimes on nature of elements and sometimes its structure, some types are defined, and in these types we'll be having number one set is column matrix. Column matrix is an arrangement of elements within third bracket or first bracket. Why is it column matrix? Because there is only one column. That means a matrix is said to be column matrix if it has one and only one column. Whatever may be the number of rows, but number of columns must be 1. Then it is called column matrix. For example, you can say this one, 0, root 3, minus 1 and half. These 4 elements consider in a single column. Or number of rows, if you say 1, 2, 3, 4. 4 rows are here. 4 rows are here. There is no restriction in the number of rows, but column must be 1. That's why it is column matrix. If you write here 10 elements vertically, no problem, 10 rows will be there. If you write 3 elements, it will be 3 rows there. If you write single element, that single row is here, single row, single column, no problem. But one column exists, so that's why it is called column matrix. And order of the matrix will be here 4 by 1. It is written as I told you, it is written as 4 into 2, but read as 4 by 1. That means first one represents number of rows always, and second component represents number of columns. So this is the order of the matrix. So since there are 4 rows, so that's why it is 4, and single column, that's why it is 1. So 4 by 1 is the order of this matrix. That means in column matrix, if you see, always this component will be 1 because the second component indicates the number of columns. So it is in column matrix always second component will be 1. So order of any column matrix will be something by 1, m by 1, n by 1, 2 by 1, 3 by 1, 5 by 1, like this. And notationally, if you want to represent, then simply we can write like this: A, capital A is the just name of the matrix, and notation is this one. This Aij represents all the elements, as I told you in the first class. This is Aij. Aij, this represents the elements of the matrix, and third bracket is given here, and besides this order is mentioned. It is complete representation of a notation of a matrix. So in column matrix always it is 1, m by n. M by n means m rows are there, number of elements m considered here theoretically, and order of the matrix is m by 1. So this is a notation to represent a matrix of any order, m by 1. Column matrix, so it is 1, m is any number. So that's much for column matrix. So similarly, row matrix. In the row matrix, you see similar concept, that is number of rows 1. In row matrix, number of rows is 1. A matrix is said to be row matrix if there exists only single row. So for example, the name of the matrix considered here B. This 4 elements are considered here, and these elements within third bracket, so definitely it's a matrix, and 4 elements are here in the row, and number of columns is here 1, 2, 3, 4. In row matrix, there is no restriction on number of columns, so there are here 4 columns are 4 matrix are 4 elements are there, so 4 columns exist. So if you consider 5 elements, the number of columns will be 5. If you consider 10 elements, so number of columns will be 10. So number of columns doesn't matter here, since it is row matrix. So only number of row must be 1. So a matrix having a single row is called row matrix. So its order definitely of the form 1 by something. Since here 4 columns are there, so 1 by 4. Second component gives the number of columns, so 1 by 4. And generally, if you want to denote this, then you can consider like this: Bij. B is simply considered for the name of the matrix B. So Bij represents all the elements of the matrix, and this is order 1 by n. Number of columns here considered generally n. N may be any number, and order is 1 by n. So this is just a notation to represent a row matrix. Very simple definition. Next, square matrix. So by the name of the type of the matrix, it is square matrix. Square. You know, square means the same dimension, length and breadth. So number of rows and number of columns, if same in the matrix, then definitely its shape will be square. So that's why it is called square matrix. For example, here you see 3 rows are there and 3 columns are there. That means number of rows and number of columns same. Any matrix having same number of rows and columns is called square matrix. So its order definitely m by m type. M by m, n by n, 2 by 2, 3 by 3, 5 by 5, 7 by 7, like this, because same number of rows and same number of columns. So that's why it is number of rows and number of columns same. So that's why it is not usually written as 3 by 3, 2 by 2, 5 by 5, m by m. It is simply order is mentioned in a single because number of rows and number of columns same. Say here 3 rows and 3 columns. So order is simply 3. So it is need not to say 3 by 3 or 4 by 4. So usually it is just said as order 3. If there are 4 rows and 4 columns, then it will be square matrix of order 4. And similarly, to denote symbolically here, Aij m by m, that's the general matrix, general square matrix is considered here. M by m, m is any number here, natural number, and this is the representation of square matrix notation. So square matrix is a matrix which has same number of rows and same number of columns. Next, another type, type 4, this is diagonal matrix. Diagonal matrix is a square matrix, basically we call a diagonal matrix if its diagonal elements, non-diagonal elements are 0. Now what is the diagonal and what are the non-diagonal? You see here, for convenience, say example C here, 3 by 3 matrix here, it is square matrix. Square matrix must be there to exist diagonal. So here number of rows and number of columns same, it is 3 by 3, so it is square matrix. In this square matrix, this direction is a diagonal direction. Left to right, left to right, top to bottom, it is this direction is the diagonal direction. In this diagonal direction, all the elements are called diagonal elements. And other than this direction, whatever elements are there, these are called non-diagonal elements. These non-diagonal elements are this position, this position, this position, again this position, and another this position. So there are these 3 and again these 3, 6. So total 6 non-diagonal elements are here, and all the non-diagonal elements are 0. Non-diagonal elements are 0, but whatever might be the diagonal elements, there is no restriction on the behavior of the elements along the diagonal, but non-diagonal elements must be 0. If non-diagonal elements are 0, then it is called diagonal matrix. In example B here, this 2 by 2 matrix. So it is so square, number of rows, number of columns same. So this is the diagonal minus 1, 2. Along the diagonal is elements are minus 1 and 2. And so these 2 non-diagonal elements are 0. So it is a diagonal matrix. Even if the number of rows and columns 1, 1, it is square matrix, number of row 1, number of column 1. So A, the first example. So this is also, we can say it is diagonal matrix. So order of these matrices, this is 1, this is order of 2, and this is order of 3. So basically, to have a diagonal matrix, we must have non-diagonal elements in a square matrix 0, and scalar matrix. In another type, scalar matrix, if you observe, then you see it is also a square matrix, but here non-diagonal elements are 0, so that's why it is diagonal matrix. And along the diagonal, whatever elements are there, these elements must be same, any constant. That means a diagonal matrix is said to be a scalar matrix if diagonal elements are same, constant. So to be scalar matrix, first matrix must be square, second it is diagonal, third diagonal elements are constant. So simply a diagonal matrix we can say scalar if the diagonal elements are constant. In this will be this of order 2 is the diagonal elements -1, non-diagonal element 0, so it is diagonal matrix, and diagonal elements are constant, that is -1 here. So it is scalar matrix of order 2, and it is similarly in case of order 1 is 3. This is also scalar matrix. Next, another type is identity matrix, very widely useful uh, definition, and in operations it will be very impactful, that identity matrix. So identity matrix is actually a scalar matrix is identity matrix if the diagonal elements are strictly one, no any other uh, elements allowed. Here in this examples, if you observe here, this is three examples are here. It is simply 1, and this of order 2, and this is of order 3. If we observe in this element, in this matrix 3 by 3 order 3, if you observe here, you see along diagonal direction the elements are fixed, constant, and that is 1. So it is scalar matrix. Constant, so it is scalar matrix. But since it is 1, so it is identity. Actually, a scalar matrix is directly identity matrix. Simply, the elements, diagonal elements should be 1. It is of order 3, identity matrix of order 3, and this is the identity matrix of order 2, and this is of order 1. And in the definition, you can say simply a scalar matrix is identity matrix if the diagonal elements are unity, 1. And symbolically, these elements of, especially for identity matrix, it's is defined very nicely here. If you observe, and this one, Aij is equal to 2 steps. It is given in 2 steps. First step 1, under condition I is equal to j. Second step, it gives 0 if I not equal to j. That means uh, if I equal to j, that means columns position and rows position if same, that element will be 1. And columns position and rows position if not equal, then that elements will be 0. So this gives identity matrix of any order. Here you say in order 3 identity matrix, here this position, if you see here, this is A11 position, first row, first column. So I is equal to 1, j equal to 1. That means the value of I and j equal. So since the value of I and j equal, so as per this definition, its value will be, that means element in this position will be 1 as per this definition. If you observe this position, what is the position in terms of notation? A12. A12. Why it is A12? It is lying in the first row and lying in the second column. So its position is A12. It's A12. That means I is equal to 1 and j equal to 2. That means the values of I and j are not equal. So if the values of I and j are not equal, as per the definition, the element must be 0. So that's why this is 0. So if you observe carefully, these positions, wherever you are getting zeros, you have seen zeros in this matrix. In all this position, I and j are different. The value of I and value of j are different. That means their positions, and column, row and column is different. If you pick up these positions, this position theoretically we write A31. This is A31. Why it is A31? It is lying in the third row, so it is 3. First column, so it is 1, 3, 1. So A31 is the position, is this one of this position, A31. So I is equal to 3 and j equal to 1. So that means the values of I and j are not equal. So as per this definition, the element in this position will be 0. So it is 0. So very nicely defined identity matrix notationally in this manner. So very much important, and in operations and in further numericals, widely useful, the concept of identity matrix of various order, especially 2 and 3 order identity matrix. Next, another type, that is zero matrix. Zero matrix is simply 0. That means when all the elements of the matrix are 0, then the entire matrix is termed as zero matrix. Here in examples, you see in the first one, single 0, that is one row, one column. In the second one, 2 rows and 2 columns are there. In the third example, 2 rows and 3 columns are here. And finally, in the last example, single row, 2 columns, single row and 2 columns. So that means dimensions of the matrices are different. That means it is not mandatory uh, to be the same. That means unlike in square matrix, so it is not necessary to be square. That means number of rows and number of columns uh, might be anything. So simply one and only one condition is there, that is all the elements of the matrix must be 0. So these 7 types are there, through which the matrix is categorized in terms of the nature of elements and number of rows, and based on number of rows and number of columns, along with the nature of its mm, elements. So these 7 types are here, and after that we'll be moving to equality of matrices. Means when we will call 2 matrices are equal, because we will be having later on some equations, and when there is equation, there will be some operations, so addition, subtraction, multiplication, and definitely in equation equality must be there. So the concept of equality, some concept on its operations, addition, subtraction, multiplications. So all this we have to be familiar to go with handling matrix equations, to be discussed later on. So I will start equality of matrices in the next session. And today simply I am giving you this much, that how to, number one, how to construct a matrix if its elements are defined. Number one. Number two, how many types of matrices are there? These 7 types of matrices we have, and we have discussed about these 7 types of matrices and how to construct a matrix if its elements are defined in functional form or to some uh, okay. So do you have any problem to understand this much just theoretically, and which will definitely help you to go through some book chapter or any thing through online, and you may go through the PDFs also which are uploaded in ERP, and you may ask if you want to say something because limited time is there for this version. Okay. In the next class, we'll be going through the equality of matrices and some operations. So that's much for today, students. Thank you
So
for
that's much for today.
joining.
Thank you for joining.
Yeah, one is just
Yeah,
waiting,
one is just
waiting in the
waiting in the
to join here.
to join here.
Okay,
Okay.
thank you so
Ballot.
much.
Thank you so much.
Yes, sir.
Equally.
Yes, sir.
Okay. Yes, sir.
Okay. Yes, sir.
Yes, sir. Bye.
Yes, sir.
Okay, sir.
Okay, sir.